Hello, this is Chemistry Paper 2 from 2018, a walkthrough for you. Question 1. Chemicals in fireworks. We're talking about metal ion colours, and we've got some recall at the beginning. What colour flame would sodium ions produce? Yellow. And a metal ion that would produce a green flame? Copper or barium. Some fireworks contain a mixture of metal ions. Why is it difficult to identify? Don't use pronouns. The metal ions can mask each other's colours. Great. 1.4. Flame emission spectroscopy. So this is the colours but seen through a spectrometer. We've got to identify metal ions in a firework, a flame emission spectrum that you have to read against a comparison of individual metal ions, which two metal ions are in the mixture. So we're going to look for the position of the lines and see what matches. We've definitely got a sodium match for these two, so the famous sodium yellow D lines are here, and then we've got something else as well. If there's a line there and it's not in our mixture, it definitely can't be that ion, so it can't be potassium and it can't be copper because those lines are not present, and it can't be calcium, those lines are not present, so we have lithium mixed with sodium. So non-metal ions are also present, so you're going to test a solution of the chemicals, and this time we're going to be doing our negative ion tests. So silver nitrate plus dilute nitric acid, and it's a cream precipitate. This is Br-. And a test to show the presence of sulfate ions, the test and the result. So add barium hydroxide solution, and you get a white precipitate. There's something I've missed, and that is first add dilute hydrochloric acid as it says in your textbook. That's to destroy carbonate ions, which would also form a precipitate. Okay, question 2. We've got methylated spirit being a useful product made out of a mixture of substances. So the name that we use for a useful product from it, this is just a definition. Formulation. And our percentage by mass, we're going to look at the table, and we've got methanol 23.3 divided by everything, and we've got some rounding, so if we've got two significant figures for only some of them, so we're going to put 7.9%. Okay, so methylated spirit contains ethanol and is available cheaply. It also contains pyridine, smelly, and methyl violet, purple. Okay, so the trouble with this thing is if it's got ethanol in it, people might drink it even though it's got methanol in it, which is a toxic substance, so we've got to discourage people from drinking it. Okay, and if you are very old-fashioned, you might use methylated spirit in a camping stove, but these days, because of the methanol content, it's not used so much, but it's an excellent solvent, so you will find it used for cleaning paintbrushes, etc. Describe how ethanol is produced from sugar solution and give the name of the process. Okay, so first of all, it is fermentation. and we have to describe it. So we have industrial process, so we're not talking about the lab here, so you don't need to talk about conical flasks or anything. So you add yeast to sugar solution, and you warm it to approximately body temperature, and in anaerobic conditions, which I hope you will remember from your biology GCSE revision as well. Okay, and you could put for several days as well. Okay then, for question 2.6, we've got some organic chemistry, and look out for this. It wasn't very much examined in recent years, so you could give that a crack in your revision and do lots of practice. So question 2.6, we've got to complete a displayed formula. It's ethanol, so it's got enough carbon atoms, and each carbon atom must have 4 sticks, and then it's got to be ol, so we need O stick H at the end, and then the other ones must be hydrogens. The gas produced when sodium is added to ethanol, so you can remember that it's a little bit like the reaction with water, so hydrogen is produced, and it's a redox reaction as well. And then what type of substance reacts with methanol to produce methanoic acid? It's an oxidizing agent, so it says in the mark scheme that you're allowed to write specific oxidizing agents, but just is the type of substance. Okay, the next question, question 3, is about the Haber process, and we've got to just recall all the details about the process. So let's just have a look. We've got nitrogen and gas X in, so that's hydrogen. Then we've got a condenser, and we've got a recycle loop back to the reactor. Our temperature is going to be 450 degrees Celsius, careful, and the pressure is going to be 200 atmospheres. Okay, and just look in the mark scheme, it does say that you've got to give your units there. Maximum 1 mark if you don't give units. The mixture of gases cools in the condenser. Why does ammonia condense but the other gases do not? So we've got a lower, sorry, my bad. It's a higher boiling point. Than nitrogen or hydrogen. Okay, and then we've got our atmosphere question. So let's just break it down. It's a 6-mark question, so let's just break down what we have to do. So we've got to explain the processes led to these changes. So you've got to say what the state change, then explain the change. Okay, so first of all, carbon dioxide levels, and it's completely fine to use formulae all the way through. CO2 levels decreased. Earth cooled. Water vapour condensed. Forming oceans. CO2 dissolved in the oceans. And then, later on, formed carbonate minerals from the shells of dead marine organisms. was trapped in sedimentary rock. Okay, and then oxygen levels increased. Once phytoplankton and green plants started to photosynthesize. CO2 was absorbed and O2 released. There you go. Now, I did say that it would be fine to write the formulae, but make sure you put the 2 low and that it's a small 2, because otherwise that would really go wrong and you'd be stuck in level 2 for not writing it properly. Okay, I haven't included every single part in here. I haven't mentioned volcanoes for a start, but perhaps it would be a good idea to put in the atmosphere for water vapour to make sure that this is a complete answer. Okay, question 3.5. Why are scientists not certain about the percentage of each gas? Okay, so there is limited evidence. So remember, when you are making a judgment about things in you're working scientifically, purple pages will advise you about this as well. Limited evidence is always a good thing to say for this style of question. Okay, and photosynthesis gives way to chromatography. We've got a student investigating colours in 3 different flowers. The colours are soluble in ethanol but insoluble in water, so let's just remind ourselves of that later. Here's the method: crush the flower, add ethanol to flower A, filter. So you've got a soluble solid is in solution of ethanol, and you're going to put spots of this coloured filtrate onto the chromatography paper and then do the same with B and C. So there's the spots on the line, lids on to prevent evaporation of the solvent, beaker because it's ethanol would evaporate too easily, spoiling your RF values. Beaker, chromatography paper, start line in ink. Oh dear, that's a mistake. And the water is below line, so that's okay. So that's not a mistake. So the student made 2 mistakes in setting up the apparatus. Give 1 problem caused by each mistake. Aha. Solvent will not dissolve the pigment. Okay, so mistake 1, water instead of ethanol. So spots will not dissolve, so will not travel up paper. And start line in ink instead of pencil. And the problem that is caused, so line will dissolve, in the solvent, so RF value cannot be calculated. Or you could say the distance travelled could not be measured. Okie doke. Question 4.2. Here's a correct apparatus, so you've got some conclusions that you can draw. Now, remembering back to previous questions, you have to say quite a lot for this. So just it wouldn't be sufficient to say C contains two colours A and B. Yeah, you just give plenty of information. So one colour in both A and B, and two colours in C. Or you could combine those all together to make one point, and you could say that in addition that they no two flowers contain the same pigment or colour. And I think it would be reasonable to assume that the examiner wanted all of this for 1 mark. So yeah, go for it. Really do give lots of information. So colour A's RF value is given, and the movement of the colour, so RF equals distance moved by spot over distance moved by solvent. So let's substitute in the numbers as we have it. So 0.65 equals 3.2 over solvent distance, and rearrangement leads to 4.9, same number of decimal places, or same number of significant figures. Question 5. Okay, rate of reaction, looks like it. Can't tell at this stage, but it does look like a rate of reaction one because it reminds us of our required practical, which you're all going to revise very thoroughly. Okay, and let's have a look. We've done lots of these type of questions before, so let's just make sure we're getting every single mark. The equation for the reaction is, we've got sodium thiosulfate, 2 moles of hydrochloric acid, making salt solution, sulfur dioxide gas, water, which is a liquid, and sulfur, which is a solid. Cloudy means a solid is present, so sulfur is produced, which is a solid. Oops. Good. Plan an investigation to show how the concentration of the sodium thiosulfate solution affects the rate of reaction with dilute hydrochloric acid. So our plan should give valid results, so that means controlled. Let's have a look at the examiner report for the question. Okay, right, so first of all, a very general point. A few candidates are using up a lot of space by repeating the question, which is not needed in an examination, and waste time and space. So this is a classic paper 2 problem, isn't it? You say a load of stuff and you haven't actually gained any marks. We'll have a look at that in the life cycle analysis question in a minute as well. But first of all, let's just make sure that we're being really precise about our independent variable, our dependent variable, and our control variable. So for this particular one, some students just carried out the experiment at 1 concentration, so they didn't give a range for their independent variable, or they varied 2 things, so they didn't have separate independent and dependent variable. And then the most common cause was omitting mentioning any variables that need to be controlled. Okay, so let's just see. So I've written a method. Let's just put that on the screen there. So let's just highlight where our independent variable, dependent variable, and control variable are in a moment. But let's go back up and draw a little diagram of this thing so that we can see if we remember it. So here is our conical flask, and it's sitting on a cross here. And you are looking at it from above, not too close, because otherwise it won't be. You'll feel uncomfortable because it's got sulfur dioxide being produced. And there you go. That's you looking at it from directly above. And here's our solution. with our thiosulfate, sodium thiosulfate plus acid. Okay, and you're going to need to time this against the clock. Okay, so that is the worst stop clock in the world. I'm going to rub that out. Okay, so what we now need to do is just identify our independent variable, dependent variable and control variable. So when we did this as a retrieval test, I think people slipped up on the independent variable weirdly, but plan an investigation to show how the concentration of sodium thiosulfate solution affects. So we have a range of concentrations. The rate of reaction, so we're going to measure time with a stop clock. And then control variables, we've got absolutely loads to do. So we've got the concentration, range of concentrations of sodium thiosulfate is what we need here. Concentration, volume, and temperature of the acid. All of those things could, using collision theory, all of these things could affect the rate of reaction. Okay, and so volume, temperature, we can measure, so measuring cylinder, and the temperature is going to be with the thermometer. Actually, I cheated and I just said to have everything at room temperature. Okay then, so the way that we're going to measure this is by when the cross disappears, so how cloudy it's going, and it's really steered you toward this, so using in our practical. Okay, and then let's have a look here and just see if we've got the independent variable, the dependent variable and the control variable really sorted out. So where are we? 25 centimetre cubed of sodium thiosulfate, so that's a control variable which I didn't even mention. So volume of sodium thiosulfate we can add in. Okay, conical flask, cross over the paper, 10 centimetre cubed, 2 molar, so there's a control variable there, control variable there. Immediately start the stop clock, so method will work. If you stop it when the cross is invisible. Okay, and you're looking through the top of the flask every time, so that's good. So swirl once to mix. If you keep on swirling it, you could do like insufficient swirling or like too much swirling, so that could affect the rate of reaction as well because you'd affect the collisions possibly. Repeat 3 times and calculate the mean time. Okay, so that is precise results, but it's not particularly valid results, it's different. Repeat the method for a range of concentrations. Finally the independent variable. Okay, and we've got the dependent variable here, but what we haven't got is any kind of description. Okay, so there's some more controls here, but what we haven't got is any description. Okay, so the shorter the time taken, the faster the rate of reaction. Now that's linked back to the question. Great. Okay, so question 6, polymers. So we've got some recall stuff about making condensation polymers. So the small molecule that's lost is water. And polypropene is produced from propene, so this is the polymer name. This is the monomer name. And when you make a repeating unit, then you show it with these brackets coming out of the sides of the you show it with sticks coming out of the sides of the brackets, and it can't have a double bond anymore, so it's just a single bond and nothing else vertically shown in the diagram changes, nothing else changes. And if you started with n of these, you get n of those. Okay, this is a nice question. Carpets are made from polypropylene and wool, or a mixture of polypropylene and wool. Okay, polypropylene, comma, wool, comma, a mixture of polypropylene and wool, and polypropylene wears out more slowly than wool. So we've got sustainability, so obviously we're going to be talking about life cycle. So any stage of the life cycle can be mentioned here when you're talking about sustainability, but we may be talking about finite and renewable resources as well. Okay, and the reason why I like this question is it's a suggest question, so you're going to get lots of marks that other people don't, and also you've got to compare the combination of the two with the other ones as well. So you compare the combination versus the single substances. Not wool versus polypropylene. So you really do have to read the question. Okay, so let's have a look at some sensible things to say. So first of all, let's flex our renewable and non-renewable. So polypropylene comes from a non-renewable source, so reduced quantity is preferred, is more sustainable. However, as it is more durable, and lasts longer, having some polypropylene means the carpet lasts longer before disposal. Okay, so that's plenty there. You can see that there's lots of things to say in the mark scheme as well. Okay, and then you've got to compare two different polymers now. So evaluate, we now know we've got to judgment is required. Okay, and it doesn't say use your own knowledge. So we can just compare. We've got lots of data in the table and it's a 4-mark question as opposed to a 6-mark question, so we're okay just using table of data, but remember you've got to have comparisons, not just quoted numbers. Okay, so we can say that polyester is denser, so harder to wear as more heavy. Heavy uniform. We've got polyester absorbs more water. I'm doing disadvantages first, I don't know why. Absorbs more water. Again, making the uniform heavier. To wear. That's going to slow you down when you're running up and down stairs. Okay then, but however, advantages? So our advantages are it melts. Let's just make sure we know what we're talking about. Polyester. No pronouns. Polyester has a higher melting point, which is safer in a fire, preventing melting. And also polyester has better flame resistance. So less hazardous to firefighter. And less damage, less easily damaged. Okay, therefore, and then you can judge. So I'm going to say that it's safer, so I'm going to use polyester. However, you could justify it the other way around, and you could say that for ease of use, then ease of wearing, you could say. But as long as you've justified it, that's fine. Okay, air pollution. Question 7. So there's a nice bit in this question which we don't often talk about, which is unburned hydrocarbons, and also global dimming comes into the mark scheme quite a lot. So older cars are tested each year to measure the amount of pollutants contained in exhaust fumes. Table 4 shows the maximum allowed percentages of exhaust pollutants for petrol cars. So let's have a look. So here's older cars and here's newer cars. And we've got that carbon monoxide, you're not allowed as much, but unburned hydrocarbons is the same. So if we're talking about engine efficiency, that's a bit of a weird one. It's probably to do with catalytic converters, I'm thinking, because that's just as inefficient as before. Anyway, we'll see. There's a little bit about it in the mark scheme. So question 7, carbon monoxide, how is it produced? So incomplete combustion from insufficient oxygen supply. Okay, and the 2 reasons why the maximum allowed percentage of carbon monoxide has been decreased. So we could say that it is toxic. Okay, so there are more stringent regulations in response to desire to improve public health so we can put respiratory health as well. Okay, and in the mark scheme it also says that it's improved engine technology, although perhaps I would debate that, or now we have catalytic converters, it's more possible to remove carbon monoxide. Okay, 7.3, one reason for having maximum allowed percentage of unburned hydrocarbons, okay, and that is to reduce respiratory illness. Or you could say cancer. But then also in the mark scheme, as you can see, it talks about global dimming, which we don't often mention, and it also says to reduce smog, which is not on your specification, but it's certainly something that happens with unburnt hydrocarbons. Okay, depending on the weather. Oxides of nitrogen are also pollutants contained in exhaust fumes. We've very recently answered this question, so describe how oxides of nitrogen are produced. So we've got nitrogen from the air, reacts with oxygen in the air at high temperatures inside internal combustion engines. So there's nothing you can do about it. It's not from the fuel. It's going to happen. So on this particular mark scheme, it's asking you to have nitrogen reacts with oxygen all for 1 mark. Okay, so now we're going to have a look at catalytic converters. Nitrogen dioxide is going to react to produce nitrogen and oxygen, so we've got a complete a equation to complete. So remembering that nitrogen is a diatomic gas, NOFCl, Br, iodine. They all are. Remember those, NOF down, and H2 as well. So we need 2 of them, and 1 of them, and 2 of them. There you go. Give 2 effects of atmospheric pollution which are reduced by using catalytic converters. So acid rain, that's why it was done originally, and then reducing respiratory illness is the big one these days, e.g. asthma. Okay then, so we've got a catalytic converter which is a mixture of 3 elements, so it's a catalyst, so we're going to be looking for transition metals. So question 8, we've got another rate of reaction question, and this time we've got magnesium carbonate and dilute hydrochloric acid, so that's a base and that's an acid, so we're looking at the production of carbon dioxide plus salt plus water. Okay, so if we've got those happening, we're going to heat it to okay, so we're changing different temperatures. We've got 30 and we've got 50. Okay, so that could affect the gas volume. Let's see what happens. Okay, so add magnesium carbonate to powder. Measure the loss of mass in the flask every 20 seconds. So they're using mass loss instead of gas volume. That's very sensible, because if you're doing 2 different temperatures, then the gas volume would change. Okay, so explain why the contents of the conical flask lose mass. Carbon dioxide is produced. And say it's a gas. Is produced. So it escapes from the flask. That's quite a heavy gas, so it would make a big difference to the mass. Okay, so we've got a plotting bit to do. Now I've done that for you, so just to remind you that it is a line of best fit which is curved. Where are we? Oh yeah. So the main problems with this line of best fit, some people didn't plot 0, 0, so make sure you plot 0, 0. The line of best fit was problematic. Some of them people assumed it was a straight line rather than a curve, so lines of best fit can be curved. Other students were penalised for double lines, or you sort of give it a bit of shading and not extending the curve over the whole range of points. So let's have a look and see if I've managed to do that on a computer screen. Okay, well, it's a bit of a wobbly line. You could do better with a pencil, especially if you hold it slightly further back than when you're writing normally. But it's definitely a curve. I've plotted 0, 0, and I've got a line that comes through all the points. So then question 8.3, we're going to do a tangent calculation. So tangents are coming up all over the place, as you can see, so it's really, really important that you know how to do this. So let's change to pointer, and we've got to draw a big old tangent, so let's put it in place at 0.95 grams, so that's just about here. It's going to be really hard to do on screen, but I will try my best to kiss the curve at 0.95. Okay, so drawing a line like this, it's got to be absolutely on the line, so it's going to be a little bit difficult to do on screen. I do apologise, there's going to be a bit of shilly-shallying. There you go. Oh no, that's too far. That's too little. I'm sorry, I can't really do this, but it should be just kissing the curve. That's too far, and that's too little, so maybe I can increase the thickness of the line or something like that to cheat. Okay, yeah, so I've cheated heavily there, but what we now need to do is make sure that it's long enough. So this would be long enough because it's overlapping there, and then you're going to do your measurements of the difference in y over the difference in x. So you're going to find the coordinates, and you're going to draw a nice big triangle, so you've got the minimum arrow. So change in mass and our change in time. Okay, so let's have a look at the angle there. So you can sort of just see that in there, that sort of angle there is about the same as that sort of angle there. So there should be enough tolerance for this to be okay, but it's a little bit difficult to do on screen. But just try and make sure that you've got the sort of roughly similar angles there. If I was being very picky, I think I would probably move my line a bit. Move my line. So change the angle just ever so slightly there, but it's very difficult on screen. Okay, so your calculation will be difference in y over difference in x, evaluated and rounded to two significant figures. Question 9. So, methanol is broken down in the body during digestion. What type of substance acts as a catalyst? Okay, so it's an enzyme. And we're looking at an equilibrium, so let's just check. Yeah, we've got some descriptions to do of what happens to the yield, and we've got to talk about effective catalyst. So it's very like a Haber process question, so let's go back and answer everything. So we are looking for the number of moles of carbon monoxide to react completely with 4.0 times 10 to the 3. So we've got one of these reacts with two of these. So we're looking for 2 times 10 to the 10 cubed. The reaction is carried out at a set temperature and pressure. The forward reaction is exothermic. Let's just check. Forward reaction makes methanol. So what happens to the yield of methanol? That's a forward reaction. Okay, and if a temperature is higher, that will reduce the yield, so the yield decreases because higher temperatures favour the reverse reaction. Because it's endothermic. Don't use pronouns. Is endothermic. Oh, keep your answer in the answer space as well. There you go. So, a pressure of 100 atmospheres is used instead of atmospheric pressure. The higher pressure gives a greater yield of methanol and an increased rate of reaction, and we are going to keep these separate, yield and rate separate in the answer. Okay, and explain why. So what should we do first? Let's do yield first. So 100 atmospheres instead of atmospheric pressure. Let's have a look at that equation again. For pressure, we're counting number of molecules. So we've got 3 molecules on this side, and we've got 1 molecule on this side. So higher pressure favours the side with fewer molecules. Yield of methanol increases at higher pressure because there are fewer molecules on the right hand side. Is that enough for the mark scheme, or do we have to say therefore the equilibrium shifts to the right? Yes, we do. Because all I've done here is repeated the question. So this is M2 and this is M1. Great. Now the rate of reaction. So higher pressure increases the rate of reaction. Oh, I'm repeating the question. So let's not repeat the question. So at higher pressure, there are more particles in a given volume. So there are more frequent collisions. So the rate increases. That's it. Okay, a catalyst is used in a reaction to produce methanol. So how does it increase the rate of reaction? So it's just defining catalyst in detail. So it provides an alternative pathway for the reaction with a lower action, with a lower activation energy. Okay, so let's just remind ourselves with our graph. So if it was an exothermic reaction, here would be a reaction hump, and here would be the alternative pathway. And just reminding ourselves one more time that we've got the activation energy is an arrow, not the hump. So activation energy with a catalyst, activation energy without a catalyst, reactants, products, enthalpy or energy. Okay, suggest why a catalyst is used in this industrial process and do not give answers in terms of increasing rate of reaction. Rubbish examiner descriptions here. So if you set the questions properly, you won't have to say do not. But so let's obey what the examiners have put themselves in a corner with, and we're just going to say lower energy costs. Okay, costs in a bracket, you don't have to put lower energy requirement. It's also fine. So suggest the effect of using the catalyst on the equilibrium yield. No effect at all. Catalysts don't affect yield, only rate. Okay, question 10. For this life cycle analysis, we do need to provide a judgment. We do need to make links between all the different aspects of the life cycle and how they affect the environment in order to approach level 3. And then I've redrawn a life cycle analysis here, so extracting, manufacturing, using, and then I've got recycled so that we've got a closed loop for life cycle analysis. That's fair, but also we've got disposal, which could include landfill instead of reuse. So landfill or burning. So burning is going to be pretty important here, because the reason why I put it here is that it does mention burning here. So let's just include that in our disposal routes. Okay then, so I would say for level 3 it would be a really good idea to mention every single stage of the life cycle and try and link that to the table, plus your own things that are not in the table, such as transport. So in manufacture there could be transport here, transport anywhere, so we can include that as well. Okay then, so let's start with extracting the materials. So we have crude oil is finite. Therefore, polystyrene is a non-renewable. Okay, whereas wood can be renewable, not always, but wood involves deforestation, and there may be, so this is my extra knowledge, be a lot of wood waste. Requiring extra disposal. Okay, I think that's plenty about extraction. Now let's talk about manufacturing. So manufacturing, and let's make as many comparisons as we can. Manufacturing requires more energy. Per cup for wood. So this may include additional energy to transport the paper cups, because they are heavier. Than polystyrene. Okay, is that enough about manufacturing? Let's have a look. The mark scheme is also talking about packaging requirements are similar. Okay, so it's got some similarities that are not in the table, so that could be an extra thing that you might like to mention. Okay, where are we in the life cycle? So we're using it. Okay, so we can say in use they're both single use. So neither has an advantage. So disposal disposal. That is ridiculous to say polystyrene is recyclable. That is dumb. Nobody can oh, yeah, that is dumb. But obviously you just got to answer the question. So if neither is recycled, then landfill or burning is better for paper cups because they are both biodegradable and release more energy. When burnt, however, this does not recover the material. Material for reuse or recycling, as this life cycle analysis suggests is possible for polystyrene. It's biased. Okay, and then also about disposal, is there anything they both cause litter, they both cause pollution, so they both cause of the environment as unsightly litter. Litter that causes high transport costs for disposal. Now, I'm just painfully aware that I haven't talked about climate change or global warming too much. So let's have a look. Where could I fit that in? More energy per cup for wood, additional energy. Okay, yeah, I should definitely put something in. So to say, so this increases global warming. If fossil fuels are burnt. Yeah, got to include it somewhere. Probably as a star, actually. So, yeah, but I've run out of space. Big writing. Okay then, so I think that is a 6-mark answer because it brings in your own knowledge. Is it? No. So, overall, paper cups have better potential to be sustainable, so we've got to make a judgment. Sustainability if their disposal is to landfill for both. I would say that's a reasonable justification, but you could justify it a little bit more and just summarise your things. So you could say, despite higher energy use. Okay, or you could justify it the other way around by saying higher energy use but overrides disposal, your choice. Okay, so the energy needed to produce 1 kilogram of coated cups, it says that we've got a mass of 1 cup is 8.3 and the energy to produce 1 cup is 550 kilojoules. So we've got 1,000 times 550 divided by 8.3 grams. So we've got an energy of 6.63 times 10 to the power of 4. Okay then, and our last question. Melamine is a polymer used to make non-disposable cups, and it does not melt when heated. Okay, so let's just use our knowledge of polymers to say that it's a thermosetting polymer. And then I just want to refer you back to the examiner report, as it says that people have got some problems. Hang on. Oh yeah, do evaluate, make a judgment about these paper cups. And then rate, we've also got, okay, and thermosetting polymers, yeah, here we go. So it says many students tainted an otherwise good answer by referring to intermolecular forces alongside a reference to crosslinks. Crosslinks are covalent bonds. Okay, that's it. Thank you, everyone.